All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Dr. Andreea Bobu, who is a research scientist at the Boston Dynamics AI Institute, and also very excited to say she's an incoming assistant professor at MIT. So at some point we will meet in person. I'm very happy about this. Something about Andreea. Andreea earned her bachelor's degree in computer science and engineering from MIT, and then moved to the other side of the country to obtain her PhD in electrical engineering and computer science at UC Berkeley, working with Anka Dragan. Her work is at the intersection of robotics, machine learning, and mathematical human modeling. And more in particular, she studies algorithmic human-robot interactions, focusing on how autonomous agents and humans can efficiently and interactively arrive at shared representations of their tasks for smoother interactions and also more reliable interactions. As you've seen in the bio I provided, she has won a number of awards, and she is very active on different communities. And today's talk is titled "Aligning Robot and Human Representations." This is personally a very exciting topic for me, and I also think this is a great one for this seminar series. And that's why I'm very happy to give you the stage, Andreea, and hear more about it. And also, before I forget, feel free to ask questions in the chat. We will try to monitor it during the talk. So
thank you. That would be very helpful.
Yeah. Please go ahead. Thank you.
Awesome. Well, thanks so much for the introduction. Very excited to virtually be here today to share with you a little bit about my work on aligning robot and human representations. And this is me in a nutshell, pretty much. I develop robot algorithms that learn from people, from a variety of different forms of data from them. And I do that because I really believe that if we want robots to not just live in a vacuum, they have to be capable to adapt and learn from the people that they interact with. And as a running example throughout this talk, we're going to have a look at this robot, let's call him Jaco, that wants to carry this mug over to my colleague here. And so it generates a trajectory xi to do so that trades off between different features of the task, things like the cup orientation, the distance to the table, efficiency, and so on. So initially, Jaco starts off only caring about being efficient, so it follows the shortest path trajectory. But then I noticed that Jaco is carrying the cup a little bit too high above the table. So I can push on it to correct it. And now the robot can use my correction to adapt to how I wanted the task to be done and stay closer to the table to hand over the mug to my colleague. So this is one example where robots can use human feedback to adapt to people and to the way that they want their tasks to be done. And I recently finished my PhD at Berkeley, where I was on this AI floor with lots of brilliant people who similarly think about getting robots to do hard tasks for humans. And here they wanted to make a robot butler that can serve wine to customers. And they came up with this. Now, from an AI perspective, this is a really amazing feat of robotics. You have this robot that's able to carry this glass incredibly fast without spilling a single drop of wine, without breaking the glass. From a human user perspective, though, I don't know about you, but if this is what the robot did around me as a customer, I would be pretty terrified. So while this robot achieves something really impressive, it fails to consider that a real customer would be probably too terrified and not satisfied of with the robot's behavior because they would be too scared of the robot spilling or breaking the glass to have a good time. And so we're seeing all of this amazing progress in getting robots to do hard tasks for people, but they're managing to do them really well in isolation, but fail once you actually put them around people. And we sort of see consequences of this in the news all the time. On the left, there's this newspaper article of the Uber crash in Arizona, where the autonomous car fatally hit a jaywalking pedestrian for the simple reason that it didn't recognize the wild notion of jaywalking pedestrians. It only knew about pedestrians at crosswalks. And on the right-hand side, you kind of have the flip side, where this time the human pilot didn't know about this new feature that was designed into the flight control system. They couldn't understand what the system was doing, which caused them to enter a tug of war, ultimately nosediving into the ocean. So human-robot interaction is still really hard. And to understand the reason underlying all of these failures that I've been talking about, I'd like to share with you an example of failed human-human interaction.
Okay. Does this row have more quarters? Does this row have more quarters, or are they the same?
The same.
The same? Okay, now watch. Now, does this row have more quarters? Does this row have more quarters, or are they the same?
That one has more quarters.
That one has more quarters?
Yeah.
Why does that one have more quarters?
Because it's stretched out.
So here this child is clearly missing something, right? He's missing this concept of conservation of certain properties like count. That's very normal for a child this age. That takes a little bit longer to develop. But without understanding this concept, the child is making the wrong inferences or he's giving the wrong answers. And not only that, but he's then also able to explain his wrong answers by using all these other concepts that he knows about that are actually pretty unrelated. In that sense, our robots are still a little bit like little children. Let's say that this time I want the robot to not carry the cup above my personal laptop, and so I can push on it. But the problem is the robot has no notion of distance from laptops. So now my push accidentally makes it learn something else. It makes it learn to stay closer to the table. So there's two problems going on here. First, without the right feature representation, the robot can't learn what I want, which is to stay away from my laptop. But even worse, it also tries to map my input to something else that it knows about, in this case, distance to table, similarly to how the child was latching onto all these other concepts to answer the researcher's questions. So in my view, one of our biggest obstacles to successful human-robot interaction is the fact that these representations between humans and robots are more often than not misaligned. And so in the past few years, I've been working on tackling what I call the representation alignment problem. How can we make sure that the robot can align its representation with that of the human that it's interacting with and learning from? And so far, we've seen a more traditional solution, a traditional approach to this question, where we have a system designer that uses their domain knowledge and expertise about the state S to just handcraft and hand specify these feature representations phi. And then the robot can learn how to do the task on top of these, for example, as a reward function R, parameterized by this blue trade-off parameter theta. And it learns this trade-off from human input about the task, like the corrections that we just saw, or there's many other kinds of input from the human, like demonstrations, teleoperation, language, and so on. And then to act in the world, the robot optimizes this reward function and produces a trajectory. So this is all fine and dandy, but the problem that we saw was that it requires you to specify everything in your representation ahead of time, which is just simply unrealistic. It's pretty unreasonable to assume that a system designer can think of what any human for any task, for any environment could possibly care about ahead of deployment. So you might say, well, there's a simple solution to this, Andreea. Why not just learn the features at the same time? After all, that is the main thing that deep learning revolution has been promising us that it's able to do. Well, let's try this and see what happens. So in this example, if the person cares about keeping the cup close to this table we just saw and away from the laptop, spatially, we could think of the reward function as looking something like this, where the lowest reward in yellow is right above the laptop and high above the table, and it gets better the closer to the table and farther from the laptop we look. Now, when the robot is missing some features like the distance to laptops, deep learning tells us that we can just model the missing feature as a neural network and concatenate it with what we already know, collect a few demonstrations of how to do the task, and then use these demonstrations to both extract what's missing implicitly and learn the reward function kind of all at once. And so this is what happens. It turns out that when we do this, we vaguely learn that being around the laptop is bad, but we don't really learn these fine-grained details of the reward function that the ground truth reward has. Now, why is that? Well, these demonstrations that we collect from the human, they're meant to teach the robot how to do the task. They aren't meant to teach the robot about the features per se. And so with this neural network structure, the method is only hoping to implicitly kind of learn and pick up along the way about this missing feature from the demonstrations. But by trying to both extract the salient features, the features that are salient for the reward function, and learn the reward function on top all at once, deep learning ends up generalizing pretty poorly. The implication is that now, if I take this reward function and optimize it to produce a trajectory, I get this behavior that's pretty suboptimal in contrast to how I would want the task to be done. So as kind of a quick summary, we have one paradigm that learns good rewards pretty quickly, but requires handcrafting this representation. And then you have another that avoids feature specification by hand, but does a pretty poor job generalizing. So my question here is, can we somehow bridge the gap here? Can we get the best of both worlds and have some learning involved, but recover something that's more structured and salient that can help us recover better rewards? So rather than assuming a handcrafted representation or just hoping that you'll pick it up along the way, a core idea in my work has been that robots should just directly engage with the human to have this interactive process for learning a shared representation. And in my work, this has led to a divide and conquer approach to the robot learning problem. So the idea of divide and conquer was, what if we first focus explicitly on learning the representation from human input, and only then use that representation for learning how to do the task as a reward function in robot learning. So what's nice about this divide and conquer philosophy is that this means that I don't have to rely on inputs that are designed to teach you about the representation implicitly, like the demonstrations that we just saw. And instead, I actually have this opportunity to design this new representation-specific input that's designed to explicitly teach you about the representation, and can do that effectively. So throughout my work, I've studied how to formalize representation alignment in human-robot interaction through a variety of different research directions. And today's talk focus will be on this divide and conquer approach that I just introduced to this divide and conquer approach to representation alignment for robot learning. So we're kind of going to go through 3 parts in this talk, and we're going to explore first, how can the robot learn about human representations? How can the robot even know when its representation is misaligned with the human in the first place? And finally, once it learns this human-aligned representation, how can it then use it to learn the downstream task and interpret the human's guidance for the task? So let's begin with the first. And as a note, I'm probably going to spend the most time on this first bulk of work. And let's come back to this example that we saw earlier, where we had a deep inverse reinforcement learning, or IRL method, that modeled the missing feature as a neural network mapping directly from the raw state of the robot, added it to the set of known features, and then learned both the representation and the missing feature and the reward kind of all at once from demonstrations. So what if, instead of trying to do this whole procedure all at once, we applied our divide and conquer philosophy and first focused on just the feature on its own and tried to learn the feature from some sort of mystery representation-specific input that I'll tell you about in just a second, and only then tried to focus on learning the reward on top of the feature set using demonstrations or corrections as evidence for the task. So that's what we're going to do. But the key question is, what is this representation-specific input that I keep saying is going to solve all of our problems? Well, one idea is to still model the missing feature as a neural network, but then you can just naively ask the person for labels representing the feature value of the feature that you're trying to learn at different states in the state space. And then you can use that for a simple supervised learning procedure to train your neural network. There's a couple problems with this. First, to cover the whole really high dimensional state space, you would need a ton of data from people. Otherwise, you would not learn something that generalizes because you would be out of distribution. And that's obviously very burdensome. We can't just ask humans for thousands and thousands of labels. But another problem with this is that people are actually pretty notoriously bad at labeling states directly. Like something like 0.32 isn't particularly intuitive for us. It turns out we can solve this second problem by instead asking the person to provide relative labels that compare the feature value in pairs of states. So I just tell you, this is better than this, this is better than this, this is better than this. So that means I don't need to give you 0.32. I just say, this is better, which is a lot easier. But even so, and we can incorporate this data set of comparisons in a model that's called the Bradley-Terry model for pairwise comparisons, and then train this with supervised learning. But even so, you still have the first problem, which is you still need a lot of comparisons to span the space of the robot. So my take on this problem was that humans are actually a lot more intelligent and capable than just giving 0, 1 labels, so long as we give them the right way to give us data. And so what I wanted here was to come up with some new type of human feedback, one that is really informative for the robot, but that also doesn't place too much sample complexity burden on the human. So the idea here was that we can pack a lot more information if we ask the person for a sequence of states with feature values that are monotonically decreasing. We call a sequence with this property a feature trace, and we're going to get into the weeds of this in a little bit, but now the robot can automatically extract comparisons from this trace by exploiting the monotonicity. So before I go into the meat of how this works, I want to show in practice what a feature trace looks like. So in practice, to teach the robot about distance from the laptop, I start somewhere where the feature is really highly expressed, so right above the laptop. Then I move the robot monotonically towards a place where the feature is not highly expressed, so away from the laptop. And after the robot collects a few of these traces that span the state space, it can learn a feature function that's defined by them. Okay, so now I like to dive a little deeper into how the robot actually takes advantage of this structure that's inherent to feature traces and uses it to train the model with the Bradley-Terry model. So first, we know that feature traces satisfy the monotonicity assumption because we know that the feature values decrease along the states of the trace. What this means is that I can take any ordered combination of two states along the trace and label them as one because it's an ordered tuple, and because I know that the first state in the tuple should have a higher feature value than the second one. What's really special about this is that for every single trace, we end up with a number of tuples that's quadratic in the length of the trace, which is a ton of data. So for every trace that takes me like 2 seconds to give, I end up with 200 or 300 comparisons, which is a ton of data to get from such little effort on the human. Another thing that we know is that we can relate the feature values across traces because we know that all traces approximately start high and end low. So what this means is that for any 2 traces, the feature values for the starts have to be consistently high, and the same for the ends, they have to be consistently low. And what this means is that we have these equivalence tuples now with a label of 0.5 that symbolizes equal probability between the starts, equal probability between the ends. So now we can incorporate our data set of monotonicity and equivalence tuples into a simple cross-entropy loss based on this Bradley-Terry model up top and just train a simple multi-layer perceptron. So that's how we end up training features from these feature traces. Now I'd like to actually showcase some actual examples of features that we learned using feature traces from both expert users on a physical robot, aka me, as well as non-experts in a user study that we ran in simulation. And for all evaluations that you're going to see, the way we evaluated our method is we sampled a bunch of, like a very large test set of states in the robot's reachable set, and we colored them here with the color of the learned feature. So here I'm displaying the distance to laptop feature. So you see that it's yellow when we're really above the laptop, and it gets closer and closer to blue as you move away from the laptop. For easier visualization, I can also take this 3D ball of points and project it onto some representative plane, like here on the right. So when we look at the ground truth distance to laptop feature, what we see is that the projected ball decreases in intensity the farther from the center of the laptop we look. And this is what we recover when we train our feature with expert feature traces. So we recover something that's pretty structurally similar. And in fact, this result holds across 6 different features of varying complexity that we looked at. And I don't want to dive too deep into what these features are yet, but I do want to point out that all of these features were trained with somewhere along 10 to 20 feature traces, not the thousands of demonstrations that the end-to-end maxent IRL method would have required. So this is a lot quicker of a procedure. And I'd also like to share some examples from a user study, because ultimately we wanted to ask, okay, is this method something that real non-expert users can use? Yes, I see someone raise their hand.
Yeah, hi, Andrea. Just one question which is coming to my mind is that you had just explained how would you tackle, keeping your laptop in the trajectory of the robot. But imagining that you are in study and you're using books, etc., which you would be working, and then you would give a command to the robot. So how would you optimize the reward function in that case?
You're saying if instead of the reward function being stay away from my laptop, you wanted the reward function to be stay close to my book?
Yeah, I mean, it's different objects in addition to your laptop, because you're in a working mode. So you don't only keep your laptop. So and then you give a command, say you want a tea to be served, so on your table while you are at work. So basically, these are the objects which is in addition to your laptop.
Yeah.
So how would you optimize the reward function in that case? Just curious to know.
Yeah, so there's kind of 2 sides to this question. So I'll give you 2 answers. First, you could imagine that you have a feature for distance to laptop and another feature for distance to books. And then your human is going to give you corrections or demonstrations to teach you that they want you to stay far away from both of them. So you could do that. The way you learn the reward function is through standard IRL from demonstrations. I can just give you a demonstration that stays away from both of them, or I can push you, give you corrections. There's multiple different ways in which I can learn the reward function. Now, the second part of the question, or not the second part of the question, like the second answer that I'm going to give to this is you could think instead of distance to laptop, what actually matters is distance to fragile or to sensitive objects. Yeah. So you could think, oh, like, I don't want you to just stay away from my laptop. I want you to stay away from any object that I don't want to spill stuff on. So we could imagine learning a more generalizable feature that encapsulates not just laptops, but also any object that fits the description of sensitive to spill or sensitive object. So that is something that we actually started looking into. It's still currently work in progress, but we're currently actually using large language models and their priors to kind of identify how can I generalize this, or like, what was the cause of the human demonstration in the situation, and how can I use that cause to generalize my feature? So for instance, I tried this thing where I tell the LLM, hey, like the human gave me this demonstration. Why did they do that? And the LLM is pretty good at saying, oh, the human doesn't want to spill on the laptop. It seems like distance to laptop is a feature that's salient to the human. Then I ask another question, which is, what other objects would have fit this description? And the LLM is quite good at saying, oh, this could have worked for any objects that are electronic devices or even documents or books, any objects that are sensitive to spills. So that's kind of what we're using right now to expand the definition of a feature to multiple different objects. Does that answer your question?
Yes, thank you very much, Andrea. And just quickly, before I have interrupted you, just one more quick question is that since you had worked between the interface of robot and the human beings, is there any element of say emotion or anger which is also taken care in your algorithm or something like that?
So funny you say that. We actually did try to learn representations for emotion. I will show a couple slides in 5 minutes. But that's like that was for learning expressive robot behaviors, like getting the robot to do a functional behavior in a happy way or do a functional behavior in a sad way. I'm not sure if you're asking about the robot exhibiting emotion in its execution, or what is the human's reaction to this teaching experience with the robot.
No, the first one. Okay, I'll wait for that.
Yes,
fine.
Yeah.
Thank you.
Just wait a couple slides.
Sure, thank you.
I see there's
Andrea,
another.
there is a
Yes,
but it seems
there's another question in
to
the chat.
be answered already. I think you gave an answer that replied to this question already.
Okay, great.
So,
awesome.
Yeah.
So now I'd like to share some actual results from the user study. So what real people actually did. And it turns out that real people actually did some pretty sensible things. So for the laptop feature, they similarly gave these traces that start above the laptop and move away from it. And then with this data, we were able to learn a distance to laptop feature that when projected looks pretty similar to what we were seeing on the previous slide. For table, they covered the space vertically from up to down. And my personal favorite one is this proxemics feature, which is this idea that people really don't like to have things in front of their face more so than to their sides. So that means that the feature isn't just like symmetric distance to human, but rather this kind of ellipsoid shaped feature. And so what I really liked about this is that real people figured out on their own that the way to teach this is to give these traces that are longer in front of them and then shorter and shorter to their sides. So that was really cool to see that we didn't tell them about this. They just figured out that, oh yeah, this is the natural way to teach the robot. So we recovered this feature that does have this ellipsis shape here on the bottom that I described. Okay, so now instead of relying on whatever features the designer specified or trying to learn everything at once, we can learn the missing feature and get closer to what the human wants. I was going to originally talk here a little bit more mathematically about what does it mean for representations to be aligned, and we defined this specific metric recently of alignment. In the interest of time, I'm going to skip over this. And instead, I'm going to kind of get to the punchline of what we mathematically did. Mathematically, our measure of alignment ended up looking at 3 criteria that we really want from our representations. We looked at what I call recoverability. So we want to make sure that the robot's representation is actually expressive enough that you could recover the human's representation if you wanted to. And so part of the objective is that describes this is this part over here that just says, I want to minimize the distance between my robot and human representation, where the F function here just acts as a translation between the two. So if this distance is small, that means that your representation phi is expressive enough that it contains everything that the human cares about. If the distance is large, like it would be the case in the case of the handcrafted feature sets, that means you're missing something. So you could throw any F function, any amount of computation you want, you would not be able to recover the human's representation. Another thing that we cared about was minimality, meaning I don't want this representation, like I want it to be expressive, but I don't want it to have way too many features that are completely irrelevant, because that's going to make my downstream learning have a ton of spurious correlates. So this part of the equation is the one that deals with this and looks at, let's try to minimize the dimensionality of our representation. And finally, we wanted the recovery to be easy. Like, since human data is so rare and I can't have tons of thousands of human inputs, I want my recovery from phi to phi to require little human data and to be simple. And the way we define simplicity, and it has been empirically observed in the deep learning community, is by just showing that a simple linear transformation, this F matrix transformation, can take you from one representation to another. So this is kind of just the punchline. I skipped a few steps, but the observation here was that when you have these, one second. Oops, I skipped a few slides over here. All right, so when you have the feature sets, so the traditional approaches, they're minimal because they're small, but you're oftentimes going to be missing something. So you're not going to be able to recover the human's representation. And on the flip side, when you have the end-to-end methods where representation is usually just straight up the state, which is high dimensional images, you're going to have recoverability because images do have a lot of information that should enable you to recover the human's representation. But this representation is certainly not going to be easy to recover. You're going to need a ton of data because it's really high dimensional. And it's certainly not minimal. So what we did and what we just saw was we kind of acknowledged that this equation is really difficult to solve without signal about phi itself. So we just said, let's just ask the human directly for the representation rather than try to kind of go at it implicitly and not indirectly. And so that's why we were able to have these representations that are small, but that are also conducive to recoverability and easy recovery because you can expand it whenever necessary. And I see there's a couple. Okay. Let's ask at the end. Sounds good. Great. So we kind of arrived at this core idea of asking humans directly about the representation. But as I was saying, asking the human is an expensive procedure. Hence, we typically don't have a lot of human data. So another more practical principle that has shown up in my work is to try to learn a lot from a little. Now I'd like to share with you a few examples of how we did that. So we just saw this principle in action here with the feature traces, where we created this data that is packed with information, but it's super easy and fast for the person to give. But I'd like to share a couple more examples of how we can do that in practice. So first, we tried expanding representation learning to these high dimensional perceptual inputs like images or point clouds, which can be notoriously data hungry. And so here, our idea for learning a lot from a little was to still collect a small amount of labels from the person and then amplify them using simulation. So if the human wants to teach a feature like objects being near, they can label images as near or not near. And then we spawn many different other objects in the simulator and augment the person's labels into a data set of thousands of examples for free. So this is kind of what people call sim to real in the field. And it turns out that by using this kind of bootstrapping with sim to real procedure, it enabled us to learn these super robust features like objects being near or above one another that could transfer to the real world directly without any additional human data. So this is like real world partial point clouds, really challenging data. We only needed a couple hundred labels from the person, which could be done in like, I don't know, 10, 20 minutes. So very fast. We also looked at what I mentioned earlier, learning more complex, fuzzy, difficult to define features like emotion. And specifically, we wanted to have robots that can exhibit expressive behavior, like tiptoeing to its goal when afraid or stomping aggressively when angry. Emotion, though, is very subjective, so it's very challenging as a feature to convey to our robots. But luckily, cognitive scientists have made this job a little bit easier for us. And they found that actually all emotion lives on this three-dimensional nice spectrum called valence, arousal, dominance, or VAD. And because of this really nice structure, we were able to learn the mapping from expressive robot behaviors like the ones on the right to this 3D space with just a few labels from the person. So we asked the person for labels for like, what does it mean to be afraid? What does it mean? Like, is this behavior afraid? Is this behavior angry? And we were able to learn this. And as a bonus, because this representation is very easy to plug into language models, we were able to generalize our models to novel emotive phrases that were never seen at training, like great weather today, or didn't get the offer, which correspond to would be falling on the spectrum quite close to happy or sad, respectively. Finally, we learned features by using common sense priors from large language models, or LLMs. And in this last example, we had a human demonstrate throwing away the can in 2 different scenarios. And then after the fact, we asked the robot, hey, robot, why were these 2 demonstrations different? Why were these 2 behaviors different? And to us, people, it's pretty common sense that the person just didn't want to step on electronics. So the feature distance to electronics is important. So we wanted to imbue the same sort of common sense reasoning into our robot. And it turns out LLMs are really good at capturing this common sense reasoning. And they were very good at identifying this hidden common sense reason of avoid electronics, even though the human didn't say anything about it. Just from looking at the two demonstrations, it was able to identify, yes, this is the thing that you are missing. And so we equipped our robot with an LLM, and it was able to then generalize its learned behavior to these new unseen situations without any additional human data. So it's still avoiding the laptop, avoiding electronics, despite the fact that it never saw laptops at training time. All right, so now that we've seen all these different clever little tricks for how to enable humans to efficiently teach individual features of their representation, I'd like to explore how would the robot even know that its representation is misaligned in the first place? How does it know that it's missing something? And so to dive deeper into that, I'd like to go back to this example from the beginning where we looked into how Jaco can learn from my push, and I'd like to dive a little deeper into what's happening here behind the scenes. So recall that Jaco starts off with this initial reward function and the resulting trajectory. And for simplicity, let's assume a linear reward function to make things simple. So remember that I'm unhappy with this behavior, so I corrected with a push down. So now to update the theta, the blue parameter, the robot propagates my correction throughout this trajectory and obtains this human preferred trajectory in orange xi-h. So now the robot can use this xi-h to update its objective theta in this gradient-like formula, where the step in the gradient is kind of guided by the induced feature difference between the induced human trajectory, the xi-h, and the original robot trajectory that was corrected, xi-r. And this gradient update lets the robot learn the correct data on the distance to table and learn to do the task the way that I wanted. Now, when I want the robot to stay further away from my laptop, with this learning algorithm, the robot would still sense this feature difference that my push induces for distance to table. And that's why it incorrectly learns to stay closer to the table. Because despite the fact that I didn't intend to teach it to stay closer to the table in this particular instance, you still sense this delta in the distance to table, and that makes you incorrectly learn to stay close. I don't want this to happen, so how do we fix that? Well, let's have a closer look at what's happening here. So let's look at the distance to table feature. And specifically, if this is the delta phi, the feature change that I was trying to induce, I would have probably just done something like this instead, because it induces the exact same feature change delta phi with a whole lot less effort. So the fact that I didn't do that means that I probably wanted something else. So our insight here was that if the human input seems to waste effort for any candidate reward function, chances are that we don't have the right space of reward functions, or in other words, we don't have the right representation. Now, to interpret waste of effort mathematically, we employed a common model for how people behave called the Boltzmann-Noisily rational model, where we assume that people select inputs AH in proportion to their exponentiated reward. What's really interesting about this model is this coefficient beta over here, which kind of dictates or models how rational or optimal the person is. And to explain what I mean, let's focus on that interaction point. And let's say that we have a reward that's high for pushing down. So if beta is 0, what this means is that this distribution is going to be uniform because everything is just zeroed out. So every single action appears as equally likely. But on the other end of the spectrum, if beta is infinity, the input that has the highest reward is going to dominate this distribution. Just mathematically speaking, if you are to plug in this beta into this equation, the only term that survives is the one that has the highest reward. So in general, you can think of beta as regulating how peaked this distribution is. And it can be thought of as rationality because if it's low, if beta is really low, everything is going to look really random. But if it's really high, the distribution is going to look very certain. How does this help us? Well, typically in robotics, beta is fixed to something reasonably high, essentially assuming that the human is going to be rational and their input should be trusted. But since we're specifically trying to detect misalignment, we're not going to do that here. And instead, we're going to estimate it and reinterpret it as a confidence in how much the robot can explain the human's input or their supposed waste of effort. So going back to the interaction point, what this means is that if the human chooses an input that is highly likely under this reward, then the robot should have high confidence in its ability to explain what the human is doing, because this makes perfect sense if this is the reward that I think the human is optimizing. But if the human does something like this instead, given what it knows, the robot should be pretty unconfident about what the heck is the human doing here. Why is the human doing this? Clearly must be missing something that prevents it from understanding the human's behavior. So if we look at the set of all of the human inputs that would all result in the same feature change delta phi, the most optimal thing to do is going to have the highest beta estimate, and the less optimal you become, the lower and lower this beta is. I'm going to skip over a bunch of math here, but what we arrived at here was this formula where we can estimate beta by looking at the difference between what the AH was versus what it should have been if it were optimal. And so this essentially, we can interpret it as the more waste and effort we have in this difference, the less confidence we're going to have. So what we're going to do is we can use this confidence beta to adjust how much to learn from the human's input. So this is the previous gradient update that we had. And what we did is we modified it to kind of be proportional to the confidence beta. Again, skipping over a bunch of math, but this F function here, the way it behaves is if as beta tends to infinity, so as beta is really high, this f function is going to tend to 1, which means I'm going to fully learn from inputs that I fully trust. But if my beta is really low, my f function is going to tend to 0, meaning I'm not going to learn at all from inputs that I do not trust. So what this means is that now when I push on the robot, it infers a low beta, which maps to no longer incorrectly updating this distance to table theta the way it did before. Obviously, this doesn't mean that the robot magically understands what I want yet, because it's still missing the feature. But it does mean that the robot is able to detect that it doesn't understand what I want, and it can prevent incorrect learning. Importantly, this is not something that we're hand tuning. This is something that the robot autonomously and automatically extracts. So in this particular case, it used beta by learning in proportion to it. But something else that the robot could do is, for example, it could just stop execution entirely if beta is below a threshold and raise a flag and ask for help. This could be helpful in safety critical situations where you don't want to necessarily keep executing bad behaviors. Okay, we ran a user study and we compared the two methods, the naive learning and the confidence-aware learning. And here we have a situation that I call well-aligned. Both the human and the robot know about distance to table, so when the human pushes, both methods learn correctly to stay close to the table. Where it gets interesting is when there is misalignment. So here the robot doesn't know about distance to table and instead it knows about cup orientation. So now the robot incorrectly infers that the human wants the cup to be tipped over. And so now the human has to both correct for the robot's incorrect learning and correct the cup, but they also have to keep pushing down. Meanwhile, with our method, because the robot is able to estimate this low confidence, it's able to stay robust to learning incorrectly from the human's input. Obviously, it doesn't mean that the robot knows magically how to stay close to the table. It doesn't, but it does mean that it's not incorrectly tipping over the cup like before. And I've talked about this idea of detecting misalignment when learning from corrections, but this framework is more general. We've applied it to learning from demonstrations and also to learning from teleoperation. And you can check out those papers if you're interested in them. All right, so now that we've seen how the robot can detect misalignment and thus know when to ask for a new feature, we're going to look at how after it learns this new representation, it can use this representation to interpret task input and close this loop. And so far, I've been focusing a lot on the JCO, but whether it's manipulation, autonomous vehicles, or quadcopters, when robots interact with humans, they need some sort of human model to be able to interpret the human's input and learn from it. And the model that we've seen a couple times in this talk is this Boltzmann model, this exponential reward model. Now, despite how widely adopted it is in robotics, this Boltzmann model and its predictions are not always the most intuitive and the most natural. At its core, there's this assumption that behavior is a choice amongst available alternatives. So the probability of any one trajectory heavily depends on what the space of trajectories they're integrating over is. And so here with this third and final body of work, I'd like to share with you why this assumption can sometimes have some pretty unexpected side effects and why we should instead look at trajectory through the lens of the human-aligned representation, the phi that we are learning. This is not obvious to see. It's a pretty subtle point. So we're going to first do a very quick detour into how people in econometrics have studied this problem. And we're going to see what they found in their settings. In econometrics, people really like to start from these simple transportation examples. So imagine that you would like to either drive or take the train. You have to choose between them. And so let's imagine that each option has a value of v. The simplest choice model in econometrics, the loose axiom, simply gives each option a probability that's proportional to the value that it has. And then the Boltzmann discrete space precursor, the Luce-Shepard model, simply makes that value an exponentiated reward of that option. Importantly, notice that in both of these cases, the option's value is compared against the space of all other alternative options. How does this go wrong? Well, let's suppose that you don't actually have a preference between driving or taking the train. You don't care. Well, Luce in that case would just predict 50-50 probability between the two. Now, if you have to choose between two cars and the train, Luce is going to predict equal probability again. So 1/3, 1/3, 1/3. Finally, let's imagine they have 99 of the same car in one train. The more cars are available, the less probability is assigned to the train. That seems wrong, since I don't actually care whether I drive or take the train. Well, people in econometrics really love this example because it's really stupidly simple, but it showcases this very fundamental issue with these models called the duplicates problem. Should the fact that I'm adding all of these duplicate options really reduce the other options probability by that much? Now, in robotics, Boltzmann is a direct extension of Luce-Shepard to continuous spaces. So notice that the sum simply becomes an integral here. And so in continuous trajectory spaces that we see in robotics, we don't exactly have duplicate options. You can't have two of the same trajectory. It's just one trajectory. But what we do have is a continuum of options of varying degrees of similarity to one another. Everything can be more or less similar to everything else. And so what we noticed is that in continuous spaces, this duplicates problem becomes the similarity problem, where now the probability of every human input is heavily affected by how similar that input or that trajectory is to the other trajectories in the space. And this in turn affects our ability, or the robot's ability, to properly interpret the person's input. So what we're saying here is that we need to account for how similarity in trajectories should influence their probability of being chosen. And similarity, importantly, we say, depends on the features that those trajectories exhibit, the representation as seen by the human. So what we proposed here to fix this model is we propose to limit errors due to similar selections with our less formula, where we take similarity into account with this similarity metric here. And importantly, similarity is seen through the lens of the feature representations of those trajectories, not the trajectories themselves. This is not a distance, a Euclidean distance between trajectories. This is a similarity from the perspective of how close are these, the representations, are these trajectories when you think of their representation equivalent. I would normally have a concrete example to like walk through in a grid world setting to understand the difference between these. But in the interest of time, I'm going to skip over this and just summarize that while we have this old Boltzmann model that suffers from the similarity problem, our model manages to use the human aligned representation to sort of adjust for any similarity that we have amongst trajectories. And this ultimately, we found, results in more reliable and robust robot inference and prediction. And we even ran a user study to confirm that this model is indeed closer to how people themselves make choices and make decisions. And so this model has implications beyond robotics. It can be used in cognitive science and econometrics. So now that we've closed the loop with all three components, I'd like to finally see how reward learning as a whole fares against that deep maxent IRL end-to-end baseline from the beginning. And we focus on the online setting where the robot starts off with some features, detects misalignment, it expands its representation by learning a new feature, and then it combines them all into a reward function. So we took what we call our feature expansive reward learning method, FURL, which first learns the missing feature from traces after detecting misalignment, and then learns the reward from corrections, and we compared it against the end-to-end maxent IRL baseline. And we looked at a few examples where the human cared about two features in their representation, one of which was unknown to the robot. And we varied which of the distance to laptop, distance to table, and distance to human or proxemics was the feature that was missing in the robot's representation. And this is the result that we got. We see that Furl is able to recover qualitatively some very close to ground truth reward functions, whereas Max and Tyrell really struggles to learn something crisp in causal. And so now, once we've properly aligned our representation with that of the person, the robot is able to do the task in the way that I wanted. It's able to stay close to the table, but also stay away from my laptop. I would like to end this. I know we're a little bit over time, but if I can have 2 more minutes, I'd like to end this deep dive into how robots can better learn to perform that task if they learn about representations by kind of stipulating a little bit over a few feature directions in terms of representation alignment. And we sort of started by putting forward this vision of engaging with people directly in this interactive process for arriving at a shared representation. But the work that I've talked about today has exclusively really looked at this one direction where where people teach the robots about the representation, and this is kind of basically the human is acting as a teacher, or the human is kind of feeding data to the robot. But in general, I really believe that representation alignment should really just be a cycle. It should be this bidirectional process for arriving at shared representations, because ultimately, we want the robot to not just be passive absorbers of data, we want them to be active participants in the interaction. And humans themselves, we as humans are remarkably good at this. When we coordinate and teach each other things that we don't know, we do it in this interactive way where the teacher probes the learner's knowledge, the learner explains what they do or don't know. And this is possible because we're actively trying to reach a shared representation, and we have a sort of common interface, a common language, so to say, for communicating about it. So ultimately, what I want is a robot that can do this. So what's next? Well, I think we've only really scratched the surface with teaching representation features, especially when you want to teach more fuzzy features like comfort. Feature traces aren't going to be enough, or the other types of feedback that we looked at are probably not going to be enough. So I'm really excited to look into novel types of representation-specific input, like language, gaze, gestures, and so on. That can be more natural and more efficient for teaching robots these new features. We can also imagine representation-specific tasks that are inspired by advances in self-supervised learning that humans can do to implicitly tell us about the representation all at once, rather than one feature at a time. And finally, I'm really curious about robots teaching the human about their representations as well. So I'm really curious to explore interfaces for revealing robot representations, and also using representations for explainability, for explaining robot failures. In general, I really believe that representation alignment can transform applications beyond just the robots that we've seen in this talk to any situations where humans and robots interact. And to me, all of these exciting directions and representation alignment are possible because we're explicitly tackling the representation alignment problem instead of just hoping that it's going to naturally emerge and naturally be solved. I'd like to thank all of my collaborators, and I saw a couple of questions in the chat. I'm happy to answer any questions now. Thank you.
Thank you very much, Andreea, for the very interesting talk. Let's open the stage for questions. There were already a couple of questions online, as you said. The first one was related to dynamic environments. It was related to the first part of the talks. And Rishav asks, how does this method perform in dynamic environments? Say, for instance, that the object analogous to the laptop is in a stationary object, but moves around.
Yeah, so this question, when answering this question, we need to think about the two parts of the pipeline. So first, there's the question of how does this work? How does learning the feature work if the feature that you're learning pertains to objects that are moving or dynamic? The second part of the question is, how does learning the reward work if the objects are moving. So for learning the feature, I think, so we had an example where from feature trace to feature trace, we changed the location of the laptop. So we had like the human gives a feature trace for the laptop being placed here. Then next iteration, I move the laptop. Human gives a new feature trace. Then next iteration, I move the laptop again. Human gives a new feature trace. So that's possible to do. I think the teaching experience itself assumes that you're in sort of teaching mode where nothing is moving. I would find it pretty difficult as a human to give input about something that is moving, I think. So I would need whatever I'm teaching you about to be stationary. Now, when it comes to rewards, I think that's more of a property of how quickly does the robot like replan its trajectory if the location of the objects has changed. So once I've learned the reward function, the way the robot typically executes a trajectory is by optimizing this reward function. So what this means is that if half a second later, I don't know, let's just imagine that the robot, the laptop has wheels and it's moving. Not realistic, but for simplicity of the argument, if half a second later the laptop has moved by a little bit, what the robot would need to do is it would need to perceive that change, and then it would need to replan its trajectory. But the features themselves would work as long as they are features that consider the laptop, that kind of learn to stay away from the laptop no matter where it is, rather than the laptop at a specific position, which we've looked into how to do. I hope this answers the question. If not, please feel free to ask follow-up.
Thank you. So then there was, it's not really a question, but it's more like Angelica was wondering whether your paper on emotion work was out.
Yes,
because that's
I can
indeed
pull it
very
up
interesting.
right now. Here you go.
Okay, great. Thank you very much. Then there is, Azijon has a question. Feel free to unmute and ask.
Can you hear me? Okay. Yeah. First of all, thank you for such a nice presentation regarding this your research topic. As far as I'm concerned, your research mainly focused on robots learning from demonstration. But at the same time, you also mentioned that you used large language model to interact with your robots. My question is, did you use a large language model just to communicate with the robot, or did you also use large language model to make your robot learn from large language model inputs? This is first one.
The latter. Let me answer this first. It's the latter. So we used the way large LLMs and robotics currently still works is you need to have a way to translate between robot state and potentially action into text. So we had what we called a captioner that captions your state. And so when you prompt the LLM, you're like, hey, here's my state of the world, insert the caption. And then you ask the question, hey, for instance, in that one project that you're referring to, we asked the question, hey, like, here's these two behaviors, why, again, captioned. Actually, in that particular paper, the way it worked is we gave the caption for the first state, the caption for the second state, because we had two different scenarios. And then we told the LLM, oh, by the way, the human did something different in these states. Why is that? And then the LLM responds and says, oh, well, typically people don't want to step on electronics, so the person wanted to avoid electronics. We're also currently working on a paper that we're going to submit in 2 days to Coral on a variant where we have a caption for one state, and then we ask the human for a demonstration, and then the robot optimizes its current reward function with its underspecified feature set, and likely that optimized trajectory is going to be different from the demonstration. So you have these two, you have the demonstrated trajectory and the optimized trajectory. You ask the LLM, hey, why are these two behaviors different? What is a feature that is missing? The LLM is pretty good at identifying the feature that contributes to the difference between the two demonstrations. And this is kind of an iterative procedure. Does that answer the question?
I think, yeah, to a certain extent. And also one thing that I wanted to know, what technique exactly you use to translate the human input into robot state? Because there are a number of techniques that, actually translate, because the large language model can translate from human language input into different domains, right? So which domain did you use? I'm just curious.
Are you referring in general in the talk or specifically for this LLM situation?
I mean, for example, there are state machine and there are behavior trees that actually the robot can, understand as a language, but the human language actually is going to be converted into those domains and then robot can perceive. So this is
Yeah, so we're not doing state machines or behavior trees or whatever. Everything is an MDP or a POMDP. Everything is sequential decision-making Markov decision processes. So in terms of how do you translate from human input to the robot interpreting that human input, that's done with that Boltzmann model that I kept mentioning in the talk. Basically, the way robots do that is they need a model, a probabilistic model, or a model of some sort that says P of human input given objective theta. And so that model is the one that translates from what the human is doing, like trajectories or language or whatever, into what does that mean for the theta that I want or for the reward function that I want. So the Boltzmann model is a common model that is used in much of robotics. If you do behavioral cloning, instead what people try to do is just imitate the human demonstration or the human inputs rather than try to learn this reward function. So you can also do that. But yeah, I think that if the human input is kinesthetic, like physical, like pushes, teleoperation demonstrations, you typically translate it by using this model of P of human input, P of trajectory given theta. If your human input is language, you have to do something a little bit different to kind of ground the language into what does this mean for human intents and for what actions the robot should take. But for example, like what does the language go faster translate into when it comes to the theta parameter? It's a little unclear. So that's a little bit more of an underexplored part in robotics and LLM at the moment.
I see. Thank you very much.
Thank you for the
Someone else
questions.
asked,
Yeah, can you learn
Yeah.
multiple features at the same time, or do you have to teach one feature at a time?
yes, not with all of these methods. Like a bunch of the methods that I talked about were learning one feature at a time, but we've had some other work that I didn't talk about that does actually look at learning the whole representation at once. There's a few trade-offs to this. The trade-offs are that when you teach one feature at a time, you're able to focus on kind of one. You're able to learn this very interpretable one feature after the other. So you kind of like you learn these features that are separatable, and they're like salient each on their own, and they're interpretable. Whereas when we try to learn, what we did in the other papers where we tried to learn everything at once is we basically learned the representation as an embedding in a neural network. So when you have an embedding, what this means is that you're not really able to point to a neuron in your embedding and be like, oh, hey, this is the feature distance to table. That's not interpretable. That's not what that means. So if you care about interpretability, it's a little difficult to do that, to learn the representation as an embedding. But it is a little bit more sample efficient because you know, like you don't, if you're trying to teach 10 features, I don't have to give you input for every single feature one at a time, and instead I can just give you data to learn everything all at once. But then another con of that method is that it turns out that people actually are they're pretty difficult at thinking about multiple features at the same. They find it pretty difficult to think about multiple features at the same time. It's much easier for them to focus on one feature at a time. And a pro to the one at a time approach is that since every feature is kind of meaningful and salient, you can reuse these features from task to task. So the idea would be that the robot kind of has this repertoire of features that it keeps like expanding and expanding. So yeah, I hope that answers the question. But yes, there is work that learns all the features at once. There is just a lot of pros and cons to each aspect.
Yeah, I think Imanshu said that helps. Maybe I have a final question. I don't know if others have still other questions, but it's very interesting how you get to have this nice representation. I really like the monotonicity part of it as well. One thing I wonder is, I've thought about how this could interface with other ways to specify behaviors. For instance, you might have LTL specifications, or you might have control barrier function, or a hierarchy of objectives you care about. You know, how would you interface those classical ways of specifying behaviors with these new techniques?
Yeah, I mean, you could use this sort of methodology to learn predicates, for example, in a more TAMP style approach. And actually, we kind of did do that with I know I went over a bunch of these techniques pretty quickly, but there was the one work where we learned above, like, is this over above this, or near, are these near each other? That kind of stemmed initially from a predicate way of thinking about it. I just, at the time, I did that when I was an intern in NVIDIA, and I just didn't like the predicate style of thinking about this because I was just very deep into my feature MDP land. So I kind of recontextualized it in my head as a feature, but in reality, it is kind of a predicate. It's this classifier that tells me, is this above or not above? So yeah, I think you absolutely should be able to apply some of these techniques for learning predicates, specifications. I don't know about LTL. I'm not super familiar with LTL, but it seems like it seems quite complex, even for experts, to sometimes figure out what the correct specification, LTL specification is. So I think a lot of work. I think the holy grail there would be to be able to ask an LLM to just go from language, or from language specification to LTL automatically. I think that isn't super easy to do at the moment.
Yeah.
And I think some people have been looking at, oh, can we query LLMs to give us LTL specifications? And that doesn't work super, it works a little bit, but it doesn't seem to work that great yet. And I have seen it used for TAMP specifications as well, like what are preconditions, postconditions. I've seen people look at using LLMs to generate these preconditions and postconditions and predicates and whatever specifications. And it seems like recent work from the past year that managed to recover some pretty reasonable looking specifications. So it seems like that framework might be a little bit more amenable to using LLMs or, more natural types of human feedback to do specification.
That's great. Thank you very much. Yeah, interesting thoughts for future directions. Is there any other question? All right, doesn't seem so. In case, I think in your slides you had your email. People can reach out if they have deeper discussions. For now, I really thank you again, Andreea. It's been great to hear more about your work, and also I look forward to discussing more in person.
Yeah, thank you very much for having me.
Thank you. And I thank everyone for joining, and see you all next week for the next talk.
Okay,
Bye.
bye-bye.